Hi, I'm Greg Kasprowicz and welcome to my home office. Today I got a very nice present. This is the famous Covidien ventilator, which documentation was released on open hardware license. And this is fully functioning unit. You see, it boots. It does what you can expect. It passes the internal test. You can even switch it on. Of course, it beeps that there is no exhalation valve, but otherwise it works. Let's switch it off. Of course, switching off is not easy. You have to do a special sequence of actions to switch it off. And what's interesting, I'm allowed to break it. So let's go. So let's open the box. Let's move the camera closer. Carefully. Here we have a connector for keyboard. Schematic diagram inside. What we have here? It's a turbine. It's an air fan BLDC turbine, which spins up to 70,000 RPM. It's BLDC. Here is a turbine driver. Essentially, it's a controller based on Motorola chip, which does the commutation. Essentially what you do, you need to deliver DC voltage, which controls the speed, power supply, which is this plug, and simply connect Hall sensors and windings and temperature sensor which go here. Here what we have on this connector is the speed signal, which is DC voltage, and feedback signal, which are pulses, and the main processor simply adjusts the voltage to get the correct RPM. This turbine is produced by Airfan company, which is a French company which is specialized in this type of equipment for the medical purposes. So let's take it outside if it's possible. This is the filter, which filters the air which is sucked from the outside. Here's the output this is the panel. Here we apply the pure oxygen, pressurized oxygen. Here's a alarm connector. It's a lemo, and essentially what it does, it has a relay. It should sit somewhere here. It's not visible actually. The harness goes to the CPU board. So it's a NC normally contacted collector, the relay. When something goes wrong, it's plugged to the alarm installation in a hospital. It is also possible to connect wireless extender. So instead of connecting the cable to the ventilator directly, one can somehow extend the range by putting similar small box with similar connector somewhere else, and this ventilator will communicate wirelessly. There should be somewhere here the wireless module, but it's open. Let's remove the panel, we'll see maybe. So let's remove the turbine. Turbine is under the LCD screen. So I remove the screws. And here's a LCD, which is standard LCD probably with LVDS inputs, because we have so few wires here. Let's remove this FNC cable. And here is actually the graphic card. It's primitive graphic card. It's produced by some French company, and it has a graphical accelerator. And it's not really accelerator. It has a graphical. So it's okay. So what we have, it's a CPLD which simulates the 8080 type interface with some memory, SRAM memory. Here is some CPU, which it's STM32, no, something else. Some ST chip, and this is graphic controller. What this beast does, it simply takes the commands from the 8080 type interface and then interprets them. Essentially, what you have a character-driven commands like D, like draw, then you specify the coordinates, where the line, where the dot starts, or where the character starts. So this is unit clock produced by the board produced by Claritech. It's still available. You can buy it, but due to large number of requests, the delivery time is quite long. Here is the main CPU board. It has several inputs and outputs. Here is the interface to the power management board. Here is the interface to the blower driver, and we have several sensors. This is the buzzer board, which is quite interesting because it's very complex. If you compare the function it does, it simply beeps, but it has a redundant beeper. It has a lot of diagnostic circuits. It has an independent battery with a charger, and it has a full bridge driver on it, and battery charger, DC-DC converter, a lot of stuff to make sure that even when everything breaks, there is no power supply, battery is depleted, this still will beep, and will simply set the alarm when something's wrong. Here we have a lot of interesting stuff. This is the oxygen valve. This tiny beast. Let's put some light. So this is the oxygen valve. It's standard on-off valve. This is interesting beast because this is a proportional valve, and this valve is responsible for breathing. Actually, what it does, it simply controls this. This is the place where oxygen is dosed by the valve. It's mixed with the air, and this is the air. The air goes out, and also this air goes through this valve to the port here, where external exhalation valve is connected. What this valve does, the valve is actually connected to the exhalation port, and it simply opens in such a way that the pressure does not drop to zero. The function is called PEEP, whatever it means. So what is interesting in this beast, you can see here, there's some tube. It's empty inside. There is some tiny diaphragm. It's not visible here actually. I can put some additional light on it. Where is the torch? So I found the torch, and you can see here there is a diaphragm inside. What this diaphragm does, it simply, there is one tube before the diaphragm. The second tube is after the diaphragm, and they both go to the differential pressure sensor. This is differential flow sensor, and it simply, the diaphragm does some obstacle. So the higher the speed, the air velocity, the higher air velocity is also goes through this flow sensor. It's similar flow sensor at the exhalation port. There's also some diaphragm, probably, or something like this, which simply senses, which simply makes sure that the sum of the flow goes through the sensors. And this tiny valve, it's a proportional valve. It's exhalation proportional valve, and this actual valve, depending on how much current is passing through the coil, it passes more or less air. The air pressure is measured by this air pressure sensor, and the output goes to this terminal, to this tube, which goes to the external valve. This is the symbol like this. This sensor measures the pressure at the output of before the acceleration valve to realize the PEEP function. And this sensor measures the inhalation port pressure. This is the connection for SPO2 sensor, which is this type of sensor. It is only 3 wires. Actually, it's two wires. It's simply a serial port. And so let's remove the turbine. So remove the oxygen port and remove the air source of the air for the acceleration valve. This is the turbine. This is the plus 33 volts main supply for the turbine. What we have here? BLDC driver, MOSFETs. MOSFETs are on the other side, the SMT ones. We have 3 upper side, three MOSFETs, which are low side drivers, and here are also NMOS transistors, which are high side drivers. That's why we need high side driver transistors. What's interesting here is it's NA555 chip, which what it actually does, it's a charge pump. It drives 15 volt square wave, which is then rectified and which supplies the high side drivers. It has a benefit that never mind the duty cycle is the high side driver also always supplied. So this charge pump which is here, which also works, but when we need a high duty cycle, then this charge pump helps this internal charge pump. So here we have a 3-phase motor and Hall drivers. This is the input filter. Actually, they put here a Murata embedded filter, but for some reason they replace it by jumper and inductor. No idea why. Either there was a shortage in the supply of these filters, or there were some other reasons why they did it. Okay, let's go. This is the power supply, main power supply. This main power supply is it's a XP 33 volt 3 amp medical grade switch mode power supply. To unplug it, we actually need some tool. So I remove the power supply. It's standard unit. The only difference is that these connectors are installed upside down. So if you compare with standard unit which you can buy in farm mode, nothing interesting here. This is interesting part. This is the power management board. What it does several things. First of all, it simply takes the input mains, delivers to the power supply. Here we have 33 volts. You have a DC-DC converter. This is nicely isolated DC-DC converter, which converts to, as far as I remember, to 24 volts and all the other voltages required by the ventilator electronics. Here we have under the power management board there's an accumulator, a battery. It's a lithium-ion battery in 7S42P, which means 7 series and 2 parallel configuration. There is some tiny board which connects to the battery. later on. Here's the charger, which maintains the charge, and this is some peak controller, which is its only function is to actually charge the battery, control the power supply. This unit can be supplied also from external voltage. You can connect from 12 to 30 volt, which means you can operate it even from the car battery or truck battery. It's interesting feature. It's a cover which you have to lift to switch the power off. This is to make sure that the power supply won't be switched off by accident. Probably some regulatory requirement. So what we have is this chip. It's a surprise that this is placed on the power management board. This is a USB host, and this is USB client. So this port, this tiny mini USB, is used to update the firmware in the unit, and these two USB hosts are used to plug the pen drive memory, USB flash memory, and dump the results, for example, measurements, all the parameters of the patient. This is the memory from which, it's I2C memory from which this beast boots. It's some old 16-bit processor inside, and it's connected to the main CPU via SPI. So its functionality is similar to a vinculum chip from FTDI, which can communicate and perform all the host magic. You simply send simple text messages, write to the file, read from the file, etc. This switch is used to disconnect and connect the memory. If you want to connect the programmer and program or dump this memory, you have to switch this off. If you leave it switch in off position, this chip won't boot. Here's the turbine power supply, where the 24 volt goes. And what's introduced are lever drivers, because this piece is 3.3 as far as I remember. And that's it. Nothing more. This is a fan driver. Let's remove this board. So I remove the screws. Here is the SRAM memory, which is used by the USB host. This is synchronous DC-DC converter, which is placed on an island to make sure the interference won't propagate around the board. There are two EMI filters from Murata. Look at this EMI filters. Every wire which goes out or in has a 47 picofarad capacitors and also ferrite beads on all lines to make sure this board won't be affected by the ESD or EMI. This is temperature sensor, which senses the internal temperature of the device. Nothing interesting here. This is the battery connector. Let's remove the battery as well. Battery removal is not that simple. You have to remove 3 screws. So as I said, 14, 1855, 18, 16, no, 18, 550 cells. It's 4.8 ampere hours. It has a BMS inside. It has 2 contacts, and then on one contact there is a 1-wire memory, which simply recognizes the battery is correct. Let's leave it here. So what we have here are the flow sensors. There is there's some other sensor. It's an atmospheric pressure sensor. It's not connected to everything, to make sure that we are that the patient always gets the right absolute pressure. And look at this ferrite cores which are plugged, where the wires go. These wires are from alarm unit, and there's also a serial port on it. And this wire goes to the SpO2 sensor, which you keep on your finger usually. So this is the CPU. It's quite complex. What we have, it's a main ST10F276 ST 16-bit processor. It's a flash memory. It's another flash memory. It's parallel UART. It's 16C750 from Texas. There are some bus drivers, serial memory. This memory is battery backed, as far as I remember. It keeps all the record of all the events, alarms, etc. What's interesting here? Nothing special. 3 sensors which sense the exhalation and pressures, and that's it. Let's have a look at the turbine then. Well, the turbine unfortunately cannot be opened without leaving the traces, so we have to remove all these 4 rivets and then try to replace them with screws. So I removed 4 rivets using this tool. It's aluminium, so it was easy. And this was glued, so I had to also crack open it. And I think we can replace this glue later on. And what we got here is another, to remove this glue right around. And hopefully we'll be able to open it. Actually, the rivets were not necessary to be removed because, well, it's only glued. So what we have here, it's some kind of labyrinth. The air goes through this hole, it goes through this slot, and then through this hole. It's simply probably to damp the noise. And the air is sucked here, and here is the turbine. Let's try to open it. It's not easy to open it because this glue, this is some silicone, but this one is very hard. You can see there is a turbine in it. It simply sucks the air from this side and outputs it from this side. There's a small BLDC motor in it. It's spinning at 70k RPM. It has wires which come this way and then are leaving the box here. There's some seal. Here inside there is some foam. Nothing. There's nothing more like foam. Next week I will have another ventilator with broken turbine. So I will open it because this one I don't want to break. Once I remove, this is very hard. It's not easy without breaking this glass. But see, it's standard small turbine which is sits this side. Here is the air chamber which mixes the pure oxygen and with air coming from the turbine. There is some filter here, multi-layer filter, which simply probably first of all damps the noise because this is very, very, very silent. I have the impression that the entire enclosure does the function of damping the noise. So let's try to assemble it back and see if it works after all. So I sealed the turbine with Kapton tape. Beautiful, isn't it? So it's almost assembled. I didn't put all the screws because I will open it anyway a few more times. This is interesting because this display was probably originally they originally used the standard graphical display with small resolution and later decided to switch to something else with higher resolution because this is still this 80 type interface. As you can see, there is some connector which is also used in simple graphical displays. The processor is 72F521AR9T, and yeah, this is interesting. This is exactly the part number. Altera CPLD 3064, it's 64 cell CPLD, very simple, very trivial device. It's probably to make sure that it has a memory controller, so this is probably the accepting commands. So this has a memory interface, and this makes this device, this CPLD performs a simulation of 8080 type display, old 8080 type display. Oh, let's plug it back. This is EMC filter. It also holds the cable. See, that's not trivial to make medical device. All these tiny aspects like this copper foil, which is touching the shield, all these ferrite bits, all this, see this ferrite, these capacitors, ferrite bits, all of them were placed here by purpose. So that's why it's so difficult to make and certify medical device, because all of these aspects must be taken into account. Let's plug it back. It looks like this a recent display with MIPI or something like this. I'll check later on what is this. Some screws and see if it still lives. Didn't connect the keyboard, but it's not important. It complains about battery which is not plugged, otherwise it works. Yeah, but unknown battery. It says it's a ventilator error, of course. I didn't connect the turbine. So it's working, at least to some extent.